Like, I guess the only announcement for today is that Erica had to reschedule her office hours. I forget exactly what time she rescheduled them. It's in the email somewhere, or the email archive on Sakai, and we still don't have a room for the discussion section, which is bad given that it's in a couple days, but hopefully the dental school figures it out soon. But at any rate, as you saw today, we're going to discuss graphing data. Hopefully most of this you've seen before in some form or another. The only thing that's new is how you can do it in R. And when you do data analysis, graphing your data prior to doing the analysis is very highly recommended. As noted on the slide here, the old saying about a picture being worth 1,000 words is especially true in terms of data analysis. That if, say, there's outliers or bad data points in your data, or if your data is severely skewed, or somebody entered in 1,000 when they were supposed to enter in 10, you draw the picture and you can see that immediately, but it's not the sort of thing that will be obvious if you just mindlessly crank your analysis without looking at it. And luckily with R, this is very easy to do. So I very highly recommend for future analysis in this class, before you do anything else, before you run a test, calculate a mean, calculate a confidence interval, anything, just plot the data. It's just a sanity check to make sure there's nothing seriously wrong with the data. I will warn you right now that if for finals in this class in particular, one of my favorite things to do is to give you data that has some sort of problem with it. You'll only notice if you graph it. So, you have been warned. Oh, general comments about graphing is that it's generally hard to know in advance what graph is going to give you the most information about a particular data set. You may want to try several different types of graphs, and in particular, if you're planning on writing a paper and putting the results of your graph in the paper, just take a couple, choose the one that's most informative or the prettiest or whatever. And particularly if you plan to publish your graph, or for that matter, if you plan to turn it in for a homework assignment, have the graders understand what you're doing, labeling the graph is important. So I know I'm being somewhat pedantic with saying make sure you put an x-axis label and a y-axis label and so forth, but the reality is if you submit a paper to a journal and the reviewers can't figure out what your axis labels are, if you're lucky, they'll send it back to you and demand that you fix it. If you're unlucky, they'll just tell you to reject it. They'll just reject your paper outright. So I'm not trying to be an ogre here. Labeling your graphs is a very important part of sharing the results with others. So now I'll just discuss the most commonly used graphs for visualizing data. And I should probably note in passing here, the types of graphs that you use for categorical data tend to be different than the ones that you will use for numeric data. I'll start out by describing graphs for categorical data. This is from a data set that's built into R on chicken weights, that basically they gave feed supplements. They gave 6 different types of feed supplements to a group of chickens, and the object of the experiment would see if some of the feed supplements were more effective than others. And if you want to follow along, or if you want to try this in R yourself at some point, this data set is already built into R. It's called chick weights, chick WTS, and if you do the commands that I show you in R using your own version of R, you should see the same graphs that I'll show today. So Graphing categorical data, there's a number of ways that you can do it. Bar charts, pie charts, and dot charts are the main ones. Personally, my opinion is if you're summarizing categorical data, usually a table is the best way to do it, which isn't a graph per se. It tends to do a better job of summarizing the data and summarizing it more precisely. So my personal opinion is that in terms of categorical data, really the only time it's worth using these other types of charts is if you're creating a poster or something like that, where the object of the game isn't necessarily so much to convey information as to look nice, let people actually look at your poster. And I know that's a somewhat cynical view of science, but let's be real here. So for tables and for papers and so forth, just put the data in a table. It's more informative that way. But if you want people to stop and look at your poster and want to come up with a sexier way to graph your categorical data, well, I'll briefly describe how to do that. Oh, first of all, how do you make the table in R? Well, that's relatively straightforward. The command is called table. And you'll notice that before I do anything else, I do this attach chick weights command. As you'll recall from last week, the attach commands in R basically tells R to attach a spreadsheet so that you can reference the columns of the spreadsheet by the names of the columns, a spreadsheet or a data frame as it's called in R. If I didn't do the attach chick weights command, if I had said table chick weights $feed, I would have gotten the same thing. But since I attach it first, I can just say table feed and I get something that looks like this. And it just gives you a simple count of how many chickens got each type of supplement. And there's about 12 in each group, but there were a few differences. Or there were only 10 chickens that got horse bean, 14 that got soybean, and so forth. Oh, if you want a slightly prettier way to display this data, you can do bar charts as shown on this graph here. It's the exact same idea as the table, but you just have a series of bars. The height of each bar gives you the count of the number of chickens in each group. And hopefully you've seen this before and it's totally self-explanatory, so I don't need to belabor the point too much. To create bar charts in R, the command that you want to use is called bar plot. And there's just a couple things to notice here that may not be 100% intuitive. First of all, notice that the command is bar plot table feed. You don't just say bar plot feed. Make a note of that because this is one of the most common things that people mess up on the homework assignment where I ask you to do this is forgetting to include the table there. If you just say bar plot feed rather than bar plot table feed, and well, you can try it for yourself, you will not get the correct picture. So make sure you say bar plot table feed. And you'll also notice there are these other commands here, ylab and main. ylab stands for Y label. It's the label for your Y-axis. Main is the main label atop your graph. If I go back to the previous slide here, you'll see in my R command I'd said ylab equals chicken count. That puts that label on the Y-axis saying that the height of the bars represents the count of chicken. And main, I said main equals number of chickens receiving each type of feed supplement. As you can see, main puts that little message at the top. When you're doing a bar plot, you don't need to say anything about the x-axis label. It generates this down here automatically. So, yeah, most of this I just said already. Important to note the syntax is bar plot table of feed and not just bar plot feed. And the YLab and main parameters give you a y-axis label and a heading for your graph. And if you plan to include your graph in a paper that you're writing or include the graph in a homework assignment, make sure you add those labels. Another way that you can summarize your categorical data is with pie charts, which, again, presumably you've all seen before. It just creates a circle. The size of each circle is proportional to the count of the number of items in that particular category. You can see the slice for horse bean is slightly smaller than the others, and soybean is slightly larger. And to create a pie chart in R, the command that you want is called pie. Once again, note that's pie table of feed and not just pie of feed. And once again, you can give it the main command to put a heading on your graph. Hopefully, this is all self-explanatory, so yeah. Comment on pie chart even more than these other methods for categorical data that we've been discussing. Pie charts are basically entirely eye candy, and a particularly bad form of eye candy in that they're not necessarily informative. I mean, if you do question mark pie in R to bring up the help file for pie charts, I mean, this is a verbatim quote of what it says. Pie charts are a very bad way of displaying information. I mean, that pretty much says it all. It says the eye is not very good at judging the relative size of these pie slices, so they often tend to obscure more than they illustrate. I mean, in some situations, if you want to demonstrate the one category is much larger than the other and make it look cool on your poster, maybe that's a place where you would want to use a pie chart. But my personal opinion is, I mean, bar charts or dot charts are more informative in pretty much all cases, and like I say, tables are generally even better. So I'm pretty sure that I'm never going to ask you to actually create one of these for the purposes of this class. I'm just tossing it out there in case you ever need to make one for whatever reason. The final way to summarize your categorical data is in a dot chart, and it looks like, okay, those dotted lines are still there. They're just virtually impossible to see. Not that it matters that much. The idea behind a dot chart is, I mean, it's pretty similar to a bar chart in that the distance on the x-axis tells you the count of the number of things in that category. Horse bean has a smaller count. Soybean has a larger count. You can see the x-axis gives you the count. Just another way that you can graph your categorical data in a way that people can see how many are in each group. And to create dot charts in R, the command is dot chart. Once again, you can specify an x-axis label, a heading using the main parameter, and so on and so forth. And once again, if I haven't beaten this horse to death already, you need to do dot chart table feed. If you just say dot chart of feed, then it won't work. And when graphing categorical data, some general comments are that, generally speaking, as I said, pie charts, you would only want to use them in some specific circumstances or just for the eye candy factor. They tend to not be very informative in terms of just conveying the data clearly. Bar charts and dot charts are generally better. And dot charts may be more informative than bar charts if the differences between the groups are very small. As you saw even with the chicken weights example, it looked like the heights of the bars were all approximately the same. You couldn't very easily see small differences in the height of the bars, especially if the heights of the bars were much larger. The flip side to that is that...
So is the default for that command to put the numerical values on the x-axis, or is there a way to switch it so that the numerical value is on the y?
For the dot chart command, the question was if there was a way to put the numerical values on the y-axis for the dot chart. I mean, to be honest, I'm not sure. I'd have to look at the help file for the dot chart command. I mean, my guess is that there is a way to do it. The graphics commands in R tend to be quite powerful, and you can get it to do almost anything that you want if you're willing to fight with it for a minute. Fight with it being the operative word here. Sometimes you have to do some fairly serious coding to get that to happen. It may be that there's just a parameter you can give to the dot chart command that says make it so that it's on the y-axis, and then you're done. But if no such parameter exists, you may have to do some coding, and unless you really need it for this class, I definitely would never ask you to code anything that elaborate. If you were writing a paper or something and needed some help with that, you're welcome to shoot me an email. But these dot charts, one way or another, if there's only small differences between the groups, it may be easier to see using a dot chart. The flip side to that is the dot chart can also give the impression that there's some large differences between groups when actually the differences are quite small. And if there's a large number of different categories, you may want to combine them to make these graphs easier to read. For example, I'm trying to think of one, say like it was like state where a person was born or nation. If they were born outside the US, then you would have at least 50 possible categories plus some countries as well. Creating a bar chart with 50 categories is going to be hard to read, so you may want to break it up into like Midwest versus West versus Northeast versus South, or whatever the case may be, so that it's actually readable. And as I've said before, for most purposes you're better off just using a table to summarize your categorical data anyway. Now I'm going to discuss some methods that you can use to graph your quantitative data. This you'll do much more commonly than you will your categorical data. I mean, categorical data, as I said, I usually just use tables. But when you analyze quantitative data, which is what you'll be doing most of the time, my personal opinion is before you do anything else, you should graph the data. I mean, I've been working on this big $20 million study on temporomandibular disorder. We had some 30 or 40 large data sets on 3,000 or 4,000 people. Before we did anything else, we took every single one of the variables that was collected in the study and just did a bunch of box plots, as I'll show here in a minute, just because it helped us see, now was our equipment malfunctioning? Is that why we got all these strange numbers for this particular data set? And this is supposed to be a number between 1 and 5. Why are there zeros in here? This must have been coded incorrectly. It's drawing these histograms and box plots is far and away the fastest and easiest way to identify problems in your data. Oh, I'm going to briefly describe how you would do this in R. Oh, the first way that you can plot quantitative data is with stem and leaf plots. And honestly, I'm showing this to you mainly for historical reasons. Once upon a time, stem and leaf plots were used quite a bit just because you didn't need a nice computer to draw them. It's hard to do a histogram or a box plot without a computer, but a stem and leaf plot is relatively easy. Now that we have computers and you can do a histogram in R in seconds, there isn't much of a reason to use stem and leaf plots anymore, but occasionally you'll see them in books or whatever. I'm going to explain what they are and how you would create one, just so you'll recognize it if you see it and know how to do it if you ever need to, but it's not something that I'm ever going to ask you to do. Oh, to create a stem and leaf plot, I mean, this is the description of how you do it by hand. I'm definitely not going to ask you to do this. If you do ever create a stem and leaf plot, R will do it automatically nowadays. But the way that we did this back in the dark ages before computers were common, first of all, you sort your data from smallest to largest, and then you decide on a stem. And usually the stem was everything to the left of the last digit, and the leaf was the last digit. Then you write a list of all your stems, and then for every stem you write the leaves in ascending order. And even if there's no leaves for a particular stem, you would write the stem anyway. So here's an illustration of how you would do that. This is from the chick weights data set again. The chick weights was a data frame, basically a spreadsheet with two columns. Thus far, all we've looked at is the feeds. Now we're going to look at the weights of the 70-odd chickens in this data set. Oh, if I say sort weight, I think that's a new command that we haven't examined before. Sort, just as its name implies, takes the data set, sorts it from smallest to largest. So as you can see here, in this chick weights data set, I can't read my own slide. Smallest number is 108, second smallest is 124, and so on up the line. And so to create the stem and leaf plot in R, the command that you want is called stem, where, say, stem of weight, and in this case, R just somewhat arbitrarily takes the first digit to be the stem and the last digit to be the leaf. Looks like it doesn't show the second digit at all. So basically it says when you have a stem of 1, i.e. the first digit is 1, then we look at the weights where the first digit is 1. There's 108, 124, 135, and so forth. So 108, it rounds to 110, so you go 1, 1. 124, it rounds to 120, 1, 2. 135, or is that 136? I guess that's 136. Rounds to 140, then 140, 141, 143, all around 140, so you write 14444. This is for the numbers starting with 1 and have a tens digit between 0 and 4. Then the next stem is for the number starting with 1 and having a tens digit between 5 and 9. So that would be 148, which is rounded to 150, 153 rounded to 150, then 6s and so on. Hopefully you get the idea. As I said, don't worry about it too much. This isn't something I'm ever going to ask you to do on any kind of a regular basis. Well, actually, I'm not going to ask you to do it at all, period, I don't think. Oh, stem and leaf plots, they're easy to create even if you don't have the benefit of a computer. They're relatively easy to understand. If you don't do any rounding, you can reproduce the data with perfect accuracy. In the weight example on the previous slide, R was rounding to the nearest tens digit, so in that case you couldn't. If there was no rounding, then you can reproduce your data exactly by looking at the stem and leaf plots. And sometimes you need to split the stem, as I alluded to on the previous slide. We saw before, starts with the 10, and then the ones digit between 0 and 4 starts with the 10, ones digit between 5 and 9. the stem command in R will do this automatically. And the biggest drawback to stem and leaf plots is if your data set is reasonably large, it would fill up your entire page to do this, which kind of kills the usefulness of them. So nowadays, people don't use stem and leaf plots very often, given that it's easy enough to create histograms, which tend to be easier to interpret. Oh, next way you can graph your quantitative data, as I just said, is histograms. And the basic idea behind histograms is you partition your quantitative data into bins of equal sizes here. It are split into bins of basically size 50, 100 to 150, 150 to 200, 200 to 250, and so on. And the height of each box is simply the count of the number of chickens with weight in that particular range. So in this case, we see there's probably about 7 chickens with weight between 100 and 150, 10 chickens with weight between 150 and 200, probably about 16 between 200 and 250, and so on. To create histograms, in the vast majority of circumstances, you'll want your bins to have equal width, and you also want to choose an appropriate number of intervals. If you choose too few intervals, then the histogram doesn't tell you much about the shape of the data, whereas if you choose too many, then it becomes really rough and hard to read, and a lot of them are empty, and you also don't see a shape of the data. The usual rule of thumb is that you want the smallest k such that 2 to the k is greater than or equal to n, where n is the number of observations and k is the number of bins for your histogram. For the chicken weights data, there's 71 observations, and 2 to the 6 is 64, which is less than 71. 2 to the 7 is greater than 71, so it shows 7 bins. And even then, you'll end up with bars that have a height of 0 sometime, which is kind of annoying. For practical purposes, if you just use the histogram command in R, it will choose the number of bins automatically, and it's been optimized pretty well that it almost always gives you a good histogram if you just use the defaults in R. In fact, I can remember like once in my entire life where I've had to tell R to override the defaults, and that was just because I was working with a collaborator who was really picky about this sort of thing. At least for the purpose of this class, if you just use the histogram command, I'm certainly not going to get on your case for not choosing the correct number of bins. So to create histograms in R, the command is hist, H-I-S-T. They hist weight, and once again, if you want axis labels, you can say main, histogram of chicken weights, and so on. If for papers or for homework assignments, you should be sure to include the labels for your graph. Another way to summarize your quantitative data that personally is the way that I tend to summarize the data more frequently than anything else is with box plots. That I'll explain this in more detail on the next slide, but the basic idea behind a box plot is that this line right here represents the median of the data. The top and the bottom of the box represent the 75th quantile and the 25th quantile, and the whiskers at the end go out to the most extreme observation within 1.5 times the inner quartile range of the data set. As we'll discuss later on, this criteria of 1.5 times the interquartile range is commonly used as a criteria to identify outliers, that any observation that's more than 1.5 interquartile range is above the 75th percentile is a possible outlier. In this particular case, there are no observations outside that range, so you don't see any little dots at the end. I'll show an example here in a minute of what this looks like if you have some potential outlying observations. So, most of this I just said, but recall from Erica's lecture last Friday, the median is the middle observation of the data set, that half of the data is lower than the median, half the data is higher than the median. Likewise, the first quartile of the data, which is 25% quantile of the data, means that 25% of the data is less than that, and 75% of the data is less than the third quartile. And the interquartile range is the difference between the first quartile and the third quartile. So, to interpret a box plot, the line at the center is the median of the data. The top and the bottom of the box are the third quartile and the first quartile. And the whiskers in R and in most programs, when you draw this, extend the most extreme data point that's no more than 1.5 times the interquartile range outside the box. And if there's observations outside that range, then they're indicated by a single dot, as I'll show you here in a minute. And to do this in R, the command, shockingly enough, is called box plot. Again, hopefully it's self-explanatory to say box plot of weight. And once again, you can give y-axis labels and headings just like you can with most every other graphical command in R. And one nice thing about box plots, which tends to be the reason that I use them so frequently, is that you can do several box plots side by side. And this is handy if you want to compare several different groups, like for instance, if you want to compare these different chicken feed supplements, you can do it with side-by-side box plots. This is an illustration of what this looks like on the chicken weight data, and there's basically, we're showing a box plot of the weights within each feed type, and as you can see here, there's a number, there's several advantages to plotting your data like this. For starters, it's really good for just giving you sort of a 1,000-foot overview of what's going on in your data. That here we see, okay, looks like horse bean in terms of creating large chickens is the worst supplement. Those who got horse bean were significantly lower than the others. Those who got linseed didn't seem to do so hot either. Looks like casein and sunflower the best. Then later on you can go back and do formal statistical tests to see is this group equal to this group or whatever the case may be. But if you just plot these box plots, you can see that immediately. Whereas if you sat there and compared each group one to another by calculating the means or whatever, it would take a lot longer. The other advantage of this is it's a good way to spot potentially suspicious data points. See, for sunflower feed, there wasn't very much variation among most of the chickens with that feed. They were all pretty close to the median. You can see the 75% quartile and 25% quartile were both pretty close to the median. There's very little above the 75% quartile, but there were three that were either way heavier or way lighter than the others. Now, in a data set of this size, and that's why you see these dots, as I said before, if an observation is more than 1.5 interquartile ranges, either above the 75th quartile or below the 25% quartile, it shows up on the graph as a dot. Now, I mean, in a data set this small, where the data is more or less in range, then you're probably not going to lose too much sleep over this. If anything, what's really surprising is that most of these chickens clustered so closely together, not that there were a few that were further apart. Now, on the other hand, if one of these weights were like 10,000 or something like that, unless it was Godzilla chicken, that's probably a bad data point. Or if you had a data point that's negative, that would be another indication that your data is probably bad. Yeah, as an aside, that's another favorite thing I like to do in homework problems or exams is give you something where one of the data points is negative for something where the data should clearly be non-negative, in which case it's important that you draw the graph so that you notice this sort of thing so that you can remove the bad data point from your data set. And yeah, so this is a long-winded explanation of why graphing your data like this is a good idea. And this is precisely what we did for our big study of temporomandibular disorder. Basically, we took the people with temporomandibular disorder and without temporomandibular disorder, did side-by-side box plots for every single data point that we measured so that we could see things like, okay, it looks like this variable is much higher for people with TMD than people without it. It's probably a variable that's associated with TMD, and this measure is a person's weight, and it's negative, so that's probably bad data that we need to clean up, sort of thing. Oh, to do side-by-side box plots in R, the command is box plot again, but you'll see here the syntax is slightly different. I say box plot, weight, and then little squiggly thing, feed. And again, I give a header and a y-axis label. What does that little squiggly thing mean? Well, in R, you'll see this again several times over the course of this course. Whenever you have like y twiddle x in R, that's a formula object in R. And generally speaking, when you use that syntax in R, the thing on the left-hand side of the twiddle is your outcome variable, and the thing on the right-hand side is your predictor variable. It's basically saying, I want to try to predict the weight of these chickens based on which feed they're getting. And so, hence our smartness CS says, okay, you want to predict feed based on weight, so I'll do a box plot separately for each feed category. And later on in this class, we'll use these formula objects again. Those of you who are familiar with regression, you will use this exact same syntax when you fit a regression model. If you don't know what that is, don't worry about it. We'll be discussing it in more detail later. Oh, one thing you may be wondering about at this point is when do you use histograms versus when do you use box plots. Histograms tend to give you more information about the overall distribution of the data, whereas box plots let you immediately see the median in the quartiles, and they can also help you see if your data is skewed or has extreme values. Another advantage to box plots is that if you want to compare cases versus controls or compare several different experimental conditions, that's easy to do using box plots, much harder using histograms. Though, which one you use really depends a lot on what you're trying to do with your data. Personally, I tend to use box plots more often just because, generally speaking, when you're doing an experiment, you're almost always comparing two things, and it's really nice to be able to do the side-by-side box plots, see if you see any differences that way. histograms can be useful if you're just looking at the overall shape of your data. Is it like reasonably bell-shaped, or is it bimodal, meaning that you have like a bunch of people clustered on one value and a bunch of people clustered on another value? You can see that using histograms. That's much harder to do using a box plot. So, say it really depends fairly heavily on what you're trying to show. Oh, things to remember from today's lecture. Graphing data is a good idea. It's much easier to see patterns in your data by graphing it than just coming up with a list of numbers. And if you want to graph categorical data, you can use bar charts, pie charts, or dot charts, although for most purposes you're better off just using a table. Graph quantitative data using stem and leaf plots, histograms, or box plots. Generally speaking, there's not much reason to use stem and leaf plots nowadays, but whether to use histograms or box plots depends heavily on what you're trying to do, and different types of graphs can give you different information. And I mean, if you're ever in doubt about which type of graph to use, then you may want to just use both. Just do both a box plot and a histogram, report the one that's most informative, or whatever the case may be. Any questions about anything today? Okay. Oh, and I guess I forgot to show my list of R commands. Well, not that there's a whole lot to say here. If you need a quick reference for the commands from today's lecture, they're on these slides that I put here at the end. And also explanations of the graphic parameters. XLab gives you an x-axis label, ylab gives you a y-axis label, main gives you a header, and if you want, and there's also this y twiddle x syntax, which is a formula that you'll be seeing over and over again throughout the course of this class.